from this value. We have talked about the definition of continuity in the way that all absolute zero exists of zero. That if x prime minus x is less than delta, then x prime minus f of x. Right. So the intuition here is, if you want the function value close enough, what you need to do is to make the value here small enough. So as long as here is small enough, this one is small. And you can see that you can translate it into a logical statement that x prime in b delta x f x prime equals to f of x. So in this case, it might seem like okay, so there is something. The notion of how close to a point or who's my neighborhood, it changed from the actual distance to some set, right? Because we're in the same set, so it seems like we're close enough. And this notion for you in x to y for all v y exists u. Okay. Such that x in u then f inverse f of x in b. Something like this. And this one is actually not hard to see. Just applying, because these are opens, right? So these are open, the union of open balls. If there's union of open balls, you may apply this definition. Right, so I'll draw a graph so that you can understand it better. So there's U, it looks like this. It's B. So in here we find a point. We're saying that if as long as it's in U, then F is in B. Just first construct this kind of ball. You draw back it through this. You know that as long as it's like in some point here, and
U is in X.
you're right. As long as it's in here, and the function value will be here. All right. So these are goals. Do this kind of argument. And actually, that can be stronger. that not only there exists U such that this thing happen, but Conti xy Conti and V open setting y, then I should write this, sorry. V is an open setting y. No, I should write this. X, Y, Conti, if only if for all V open Y, F inverse V is open X. So we're not only talking about there exists an open set F inverse B, but F inverse B itself is open set. Right? What's the difference here? Here we're saying that there exists an U that contains an F inverse B. But we now say that this U you can choose it to be F inverse B. And to prove this, you want to say that for this direction, you want to say that if it only if this one is Conti, and this one is open, 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 then this one is open. Okay. How do you say this one's open? Like by definition. So I want to show that for all there exists such that Vrx lies in F inverse B. Right? That's one definition. Sorry, not X. F inverse B. Right? You're trying to say this. That's just the definition of open. Do some translation. Not that hard. What is Vrx in F inverse B? We mean that x prime the x prime x, if it's less than r, then f of x prime is in B. Cool? Not cool. What's Vrx? It's the set that, okay, so we're saying that Vrx is in this set, which means that everything in this set is this set. Cool. So as long as x prime in Vrx, then x prime in F inverse B. What's this? This one means Vx prime x less than r. And this one means Fx prime in B. That's just definition. So from this you can see this chain here. How you do this is just use, we want to make this one small enough, then the f of x prime is in V, and you know V is an open set. So how to do this? Okay, so take x in f equals V. We're trying to say that there's one in V, and it's equivalently to say that, sorry, that's equivalent, but it's stronger to say that it's lying in some open ball. Because you know V is open. So there exists some, let's say R prime larger than 0, such that VR prime f of x lies in V. VR prime f of x lies in V. Right. Just so the image here be like, you know this one, push it to this point. So what you need to do is to find a ball here and put it back. You can find the ball here. Right. The intuition is pick a point. Here is a ball, so you can draw it back. Right. So you know that there is an open ball here. And you know from this definition, there exists R larger than 0 such that Rx lies in F inverse R prime F of x. This one is a subset V. F inverse V, sorry. F inverse V. There exists R BRX lies in this one. Again, the intuition here. We want to find a ball here. You push the point here. Find a ball here because you know this one's open. You can pull it back because this one's continuous. Right. Good. And how about this one? This one is more trivial because you can take V as open balls and not. Right. If you take this one as open ball, that means the definition here. Right. Take V as open balls. So you know that what is continuous? The continuous means the pre-image of open set is open. So of course the pre-image of closed set is closed. Why is that? So let's say the reason why is this is because you know F inverse F who maps to F is the one who does not map to FC. Right? So equals to F inverse FC C. Again, the one who does not map to F is the one who does not map to FC. Right? So this one is who does not map to FC. This one is who map to FC, who does not map to FC. So this one. Okay. And now this one is open. So this one's open. So this one's closed. Alright? So this one's closed. Proof is done. Okay. If G is conti, F is conti, that's like to write it down like rigorously. Conti in G, Y to Z, conti. Then G circle X to Z. Again, we use graph to see how this goes. This one's X, this one's Y, this one's Z. Alright. So you know that, what you know? You know that each open set here, 40 back is an open set, okay? So this one, if it's Z open, then 40 back would be Y open. This one is G. Alright. And F told you that any Y open set, 40 back will be X open set. So how does this goes? You just take an open set in Z. You know that 40 back will be Y open and 40 back will be X open. So there'll be this kind of proof, right? This is one way. Another way is to control the distance. And how to do that? You know that for all delta 1 here, you can find a delta 2 here. And for every delta 2 here, you can find a delta 3 here. So for every delta 1 here, you can find a delta 3 here. Right? I'll do both. There's one. U is open in Z, and the G circle F inverse Z. What's this? That is G F G inverse Z F inverse. Right. So and you know this one is open, so this one is open, so this one is open. So proof is done because this one is open. And the second proof, because you know that you want to show that all epsilon larger than 0, there it says delta, such that B delta X.
Wait, it should be U inside, not Z.
Right. Such that B delta X is in by saying B epsilon F of X. I'll mark, sorry, G circle F of X. We're using Z, we're using X. But you know that proof, there exists delta 1, that's by continuity of G. Of G, there exists delta 1 such that Vy delta 1 x, sorry, V delta 1 f of x analyzing the epsilon z you circle f of x just by the continuity of g, and again by continuity of f there exists delta 2 blah blah blah, so that the delta 2 x g, and check g inverse so it'll be g circle f inverse x rising f inverse Vy delta 1 f of x. However, you know this one, so you know that f inverse g inverse B epsilon z g circle f x. How many? Alright. Alright. So this one is this one. I will not prove that the uniform continuous like very careful, just like know the argument, and I personally prefer the rooting version of the proof in uniform continuous rather than the one Francis Su shown in the video, because like I think that's more intuitive to see why that happens or how to come up with that kind of proof, rather than to construct 1 over n this times distance over blah 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 blah. It's just like too hard. It's just like the whole concept of Labelle-Calvert lemma is to control the distance, and I think the virtual rooting presents like it gives a great vision of how to do this kind of control. It's just like, yeah, quite good. You should run through that. After this one, okay, so the compact theorem, if f x y on T, and we know A is compact in X, then f of K is compact in Y. So as I think Borsche have shown last week, if you have this kind of theorem, you can prove a lot of the existence in economics, such that you can find some marginal demand, something like that, as long as you know that the maximizer exists. And this theorem assures that the existence of the maximizer or minimizer. The proof here, let's say U, so let's say U alpha, V alpha is an open cover of f of k, and want to show that it has an finite open subcover. how to do this? We're trying, we're thinking about, like, what we need to do is to find open copy here, you want to see open copy here. Right. And you know this one's compact. So somehow you need this kind of finiteness to preserve this kind of finiteness. So this one, it assures that F1, this one is an open cover of K. Right? Right. Pull. Just pull it back. And you know, open, pull it back, will be open. So there's one open cover. And of course the cover is that. Right. So you can find F inverse be alpha I, that is finite open cover of K. So you know that you only need finite open sets to cover K. So that you know the alpha I is a finite open cover of K. Of Fk. Sorry. So the image would be like S1 is f of k. You know there is an open cover that may be infinite. Blah 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 blah. And you just want to use the compactness here to find finiteness here. And so you pull it back, and it gives you maybe infinite kind of circle. Maybe not circle, maybe just like open sets, but for convenience, let's draw a circle. And maybe infinite. And you know that, okay, somehow use this compactness, we only need finite parts. And you can cover the whole K. You can pull it back. You just pull it back and can, again, push it over here. And you know that this push over will give you open set. Why? It's because that this open set is being pulled back. So the push over of this pullback is the original open set. Right? So this one gives you finite open cover. No. So in this sense, we call like we can find that the compactness is preserved by continuous function. And in this kind of sense, we call it compactness is a topological property, but not important. All this kind of like topological. Compact. Check what I want to cover. Alright, this one, uniformly converse, uniformly continuous. So the statement would be, oh, not perfect. X, Y, X is compact. So continuous. X is compact, and you can see that f of x, that f is uniformly continuous, which means that all epsilon larger than 0, the exists a delta larger than 0, all x in x So what is it like differ from, how it differ from the original continuity definition? We bring this quantifier from the very beginning here. Right. So in like original continuity sense, you can choose delta for each x. You can choose a delta, a different delta. But in this case, you can choose a delta that suits for all x. And that's how like uniformly converge, uniformly continuous work. This kind of notion is like sometimes important when you want to control something. So like if you don't want like some part that grows too fast, you can say that, okay, we see that this one is uniformly continuous, so it would not, like globally, would not grow too fast or change too fast, because like you have a global delta to control on the function values. Yeah. That's statement, 18. There. Connect. Then X connect. C connect in X. Then C. It should be like, yeah, right. FC is connect in Y. The continuity also preserves the connectedness. And that's like intuitively it should be correct. Right? If you have a continuous function, there is something like a function of thing like it's connected. You want to push it over to a continuous function, then that should be connected. Right? Intuitively it should be correct. I have to say that because like, if you want to say that this one is connected, it means that it cannot be separated. Because if you can separate this one, it's somehow like, it seems like you can separate this one. Alright? So that's the proof. So that's the proof. Do I have time for the proof? No, I don't have the time for the proof, but you need to go through this by yourself, okay? And Larry, or do I have? I have this. Okay, maybe I have. Maybe I have. So. Proof. Again, the intuition is that if this one can be separated, then this one can be separated. All right. So let's say FC equals to A, B, that is non-empty, separated. All right. Then, and you want that this one plane. Also separated. and this one is like quite trivial because F inverse A, we want to show that F inverse B equals to this one, right? This one, what you want to show, and also the opposite way, but the opposite is like just the same as this one. And we know this one, A bar. What's this? It's because that this one's closed. Why this one's closed is because this one's closed. This one's closed, this one's continuous, so this one's closed. And the closure should be smaller than this, than the closed set. So this one's closed. And you know this one equals to F inverse A bar of B. And also the converse way. So proof is done. All right. So IBT. So if F is from X to R is a function like this, and you know X is connected. If F of X1 equals to A, and X2 equals to B, and C in AB. Sorry, continuous, I forgot continuous. Then F such that F of X equals to C. As intermediate value 0. And why is that? Because the image should be connected. There, you something like approach X, A, approach B, is approach everything between A and B. So it's just a straightforward corollary from this one. I think I run through all points. Yep. That's 10. Perfect.
Your timing is also perfect.
Yep.
It's like 30 seconds to file. Or 20 seconds.
Like someone asked me how to study math. And I think the way I have told you that you need to study like very hard, maybe like 20 hours a week. And I think another way to do this kind of thing is like, you're trying to study this subject. I think two mindsets. One is like, don't say it's a tool of economics. You just like appreciate the subject itself. It would be like study this one better, because you will not keep asking yourself what is the economic intuition of this, what's the economic intuition of that. Like, that will not praise you anything like after you should first like appreciate this kind of thing, and you absorb all of this thing, and you take this thing to see how economics going. I think that would be better. Or you will not, if you just see that as a tool, you will not appreciate the spirit, we will not learn how to operate this thing. And what's the second point? The second point is like try to think about like what is the best way for you to study this. If you want to like recap it maybe like 3 months later. So you should not learn it as a way that you should pass a test. You should learn it like you can keep this kind of thing. You will not forget maybe after 2 weeks after the final exam. And how you do this, that's kind of your job, right? So not just to memorize all the definition, all the proofs. You should like try to feel, like use your heart to feel those arguments. I know that's kind of mysterious, but try to do that. Like try to think about like why it is like so straightforward. It's not actually not complicated.
I think what someone is trying to say is that the key thing of all of this is to figure out the reasoning process that's behind all of this. And so that so memorizing the definition or memorizing the proofs just for the exam does not really help you, because you need to know the reasoning process. And this will help you because when you see other things, well, the same process will help you. And that's the whole goal. Yeah, because when you see graduate microeconomics,
Yep.
you'll see the same reasoning process coming out again. Yeah, just in different places. And if you know how to do this, then you can take out any math course. Even studying it yourself.
I'm not so sure if it's all math course, but
yeah, the claim for any needs a disclaimer, but yeah. But at least that's the gateway. What?
Yeah.
You mean Royden or?
As long as there's no like algebra, I think that'll be fine.
Well, at least okay. Put it this way: you have a gateway to you have a gateway to learn any math course.
Yeah. I'll go for this.
There's always no guarantee.
The major area is like a lot more mysterious than here. That's the algebra and that's. All right. I'm thinking about like adding you back for like maybe 15